now we're talking about basic terminology that we need to understand when we talk about graphs and want to work with them. The first and most important concept you have to understand are nodes. Nodes represent an entity or an object in a graph, and they are mathematically expressed as Vi, where I stands for the individual node that we then can further describe with additional information. So an example for that would be a brother and a sister. Both of them are nodes, and we label the brother V1 and the sister then as V2, and there we can then work with that. Sometimes nodes are also expressed as vertices, so don't get confused there on different wording for the same concept. And what you see here at the bottom, we express the node 1 and node 2. So we keep building on that graph down there with every other concept that we're adding. Because the next thing we're adding are edges and links. And edges and links represent a relationship or a connection between two nodes. So when we go back to the example of brother and sister, the edge would be the family ties between them, and they are expressed as EJ. So where the connection is here between the node 1 and the node 2. So this is something how we label that in a mathematical context. And if we have two nodes that are connected by an edge, we call them adjacent, and a concept we will later see as well more in detail. And an edge is an incident with two other nodes once it's connected. So here in this graph that we display, the edge 2 is incident to node 1. What we can also look at into graphs, or the graph as itself, is the consistency of nodes and edges together. So they are represented as the entity of both aspects. So we have the nodes here represented through V1 to Vn, and the edges with edge 1 to edge n. So all of that together combines the graph. You can't separate those things if you want to analyze the graph. You always need the nodes and the edges. And to this basic graph here of two nodes and one edge, we want to add a few things. The first thing we want to add is a loop. So a loop is, as the word says, an edge which connects a node with itself. So we return back to where we started from. And they are also then, of course, expressed as they are connecting only the node to the same node. So you have, in the expression of the edge, you have this self-reference here. We can go on. We can have an arc. An arc is a directed edge, so graphically represented as an arrow. So you see here in the graph at the bottom that node 3 is connected to node 1 only in one direction. So we have the connection between node 3 to node 1, but not the other way around. And quite often they are actually not called arcs because that is a little bit of a weird name concept here. But what we actually have is that we call them directed edges or directed links. So it's something way more intuitive here. We also have sometimes really, really weird concepts in a graph. That would be a dangling node. In case you missed it, it's down there at the bottom, this node 4, which is not connected to the rest of the graph. And so this is something really important to keep in mind. Sometimes nodes are not connected to other nodes, but they are still there and they are still important for the graph analysis. And when we move a little bit away from how to paint or draw a graph and more mathematical conceptualize things, we want to look at specific key variables. So one thing we have to look at is the degree of a node, where we have the number of edges connected to a node. So we count for every node in the graph how many connections it has. So if you think of this in social network context, you open your social media page and you see how many friends you have. This is your number of degree, and we can do this for everyone in this graph and then get a better picture of how connected people are. And really, really, really important here is that you have to differentiate between edges and neighboring knots. So, because in multigraphs, parallel edges increase the degrees, but not the neighboring knots. And this looks like this here. If you look at knot 1, in both cases, we have 5 neighboring knots. On the left side, you have the knot 1 connecting to knot 1, 2, 3, 4, 5, and 6. And on the right side, here in the star in the middle, is also knot 1. It connects also to 5 other ring knots, but it has a different number of degrees, because on the left side, you only have the connection once. On the right side, you have sometimes connection multiple times, so this is why on the left side, the neighboring knots and degrees is the same with 5, but on the right side, the neighboring knots are 5 and the degree is 8. So this is something you have to keep in mind, that this is something that neighboring knots doesn't equalize degrees if we have multigraphs. And the same really important distinction is if you have directed graphs, so if it matters in which direction the connection goes, because there we have to differ between degrees that are going into a knot and degrees that are going out of a knot. So this is really important, and to not confuse the degrees, we saw also in weighted graphs, that's the aspect. Now, we have that edges are quantified. Then we add them up, and then we get a strength. So also here, the really intuitive understanding of strength, directions, and distinguishing different concepts with different names, so not people not getting confused. The most easiest way to describe a graph is a degree sequence. So if you have the first time looking at a graph, you take a piece of paper, you list all the knots, and next to them you write the degree they have. This is all a degree sequence gives you, because it is a first aggregate understanding of the degrees in a graph. It tells you, oh, is everyone pretty much the same, or do we have some outliers? So this is the first thing, especially for huge graphs, to see how those things are connected, how the different knots are connected. And especially in larger graphs, it is really difficult to have this degree sequence written down and then go over the numbers, at least at knot 155, you're getting bored and you forgot what you looked at, so we visualize those things. The most easiest way is a degree distribution, and hang in there, we're getting back in a second with a visualization of that, where we count in the degree distribution the number of knots with a given degree. So we can reveal how evenly distributed relationships are among the knots. So we take the degree sequence and plot this visually in a histogram. And it represents the probability that a randomly chosen knot has a degree k. That is also an important aspect once we later on move on to randomly chosen or random networks, where the average or the probability are really important concepts. And not just the degree distribution is really important, also the cumulative degree distribution is of importance, because here we have the share of knots in a given graph with a degree lower than k. So also here, visualization is coming up on the next slide. But it's easier to interpret than a degree distribution, because you have the cumulative aspects of the graph, and you see how many outliers you have, where the bulk of the knots, how their degrees are. And it is also really helpful to understand the overall structure of the graph. So here on the left side, you have a random graph with 20 knots and 50 edges that we just randomly generated. And in the middle, you have the degree distribution. And you see most knots have a degree of 4, second most are of degree 6. And you see this kind of, I wouldn't say bell-shaped curve here, but you have this visualization that most of them are somewhere between 4 and 6 degrees. On the right side, you have the cumulative distribution. And there you see how many percentage have this degree or less. So 0 or less, 100% of course. All of them are connected. If you move on to degree 4, for example, 80% of all knots have a degree of 4 or less. So this is something where you see where the cumulative distribution falls down, where you see like, oh, this is really where things change. And then you see at the bottom right of this graph, well, barely anyone is up there in the top or having degrees of 8, 9, 10. Actually, 0 have that, which you can also see in this graph, in the visualization on the left. But the moment your graph gets like a real life graph and a little bit bigger, you can't see that stuff anymore, and you really have to rely on the cumulative degree distribution.